Hey, Alex. Thanks for joining us today. Yeah, so first up, we'd love to hear a little bit more about what your background is. What are some of the research topics that you're working on at Ethereum Foundation, and what are you excited by in the space?
Yeah, so as the introduction said, my current position is I'm a researcher at Ethereum Foundation. My job description is essentially form verification AI, and a lot of the motivation behind that is that we have a lot of...
Yeah, I think you have to press the... Yeah.
It's better now?
Yeah,
cool.
Perfect.
So we have a lot of kind of problems we want to tackle, which is that we have supposedly blockchains. The idea is broadly to trust the code, not humans. But at the end of the day, it's humans writing the code. Code bases, once you have many lines of code, have bugs. And so if we want to actually be able to trust the code, at some point we should have as much of it as possible to be formally verified. In particular, something that we're looking at the moment is all of the ZKVMs that are popping up,
right.
And that are really exciting because you can just have a cryptographic proof of execution of any kind of Rust program, which is exciting both for us on the blockchain front, but also actually for a lot of people outside of blockchains who might not even like blockchains, but are very interested in the idea that you can just prove execution of arbitrary Rust code. And if anyone has seen Justin's Beamchain announcement the other day, yeah. It's on the roadmap for us to have proofs of EVM. The EVM state transition function as part of that, and as part of snarkifying the EVM. So we've got a big focus on these specifically. It would also be really nice to improve the state of form verification within the smart contract ecosystem and just broadly at large. A big part of that is trying to get better tooling, trying to make things easier for people to formally verify things. There's always far more people writing code than there are people formally verifying things, and AI has made writing code much easier in many respects.
Yes.
At the moment, it hasn't made formally verifying that code much easier in any respect. So the kind of delta between both isn't looking good. And so the kind of AI part is really looking at this and trying to make AI much more useful for form verification, which can be a few things, right? It can be generating proofs of correctness for a certain program, and that's probably quite hard and probably something that we'll learn more in the future. But it might be proof repair if you've already shown that a program is correct with respect to a specification, and maybe you change a bit of the code or you change a bit of specification. Maybe AI can help you repair that proof, and then you can just push those changes through CI or something like this, and it can be kind of hopefully nearly automated with someone would check that it's actually correct. But at least if it doesn't work, you'll get an error message in Lean or whatever to improve what you're using. So you'll at least know if it's not working, and if it works, you'll know that it's worked, and you don't need to kind of look at it further. So that'd be really nice, because a lot of software that we're looking at is a moving target. If you're looking at ZKVMs, they're now deployed in production and people are using them, but the circuits might change every 6 months, every year. The proof systems might change, where we always have kind of new cryptography coming up, new proof systems that are better, which leads to new implementations, which means to new things to formally verify. And we can't always have a kind of several months gap between people wanting to deploy code and us being able to formally verify it, because at that point we'll just never have formally verified code that people are actually interacting with. We want to close that gap as much as possible, and hopefully AI becomes a part of doing that and makes our lives a bit easier. A lot of the things would be interesting. It would be really cool to have the ability to take some code written in Solidity or Python or any kind of informal language and auto-formalize it into a formal specification language that might not have manual proofs of correctness. But you have languages like Daphne or Quint that will support some kind of automated testing out of the box. And that would mean that if you're writing Solidity, you can write Solidity. If your workflow is the same as it is now, you're probably not writing many tests, and you're probably not writing a specification for your program. But then you might actually have a tool that can extract that into Daphne or Quint, have some automated testing, and then if you want to go further, you can pass that off to a form verification contractor, and at least they have tests to look at and some kind of specification to work with.
Yeah.
That would be really cool, and that I think is quite practical.
For sure. I mean, where do you think how would AI broadly change the security pipeline that we see today for smart contracts? So obviously auditing is a big industry right now. It's a big step, but it's also a bottleneck to development, and we still see a lot of hacks happening all the time. So how can we kind of use AI and these agents and all of these new formal verification tools to kind of bridge this process?
I think AI is going to help with scaling out audits. You can definitely take even something like Claude or GPT-4 right now and give it a smart contract, give it a lot of context about maybe specific kinds of vulnerabilities, and tell it to scan the contract for those vulnerabilities. You obviously don't have a proof that if it doesn't find anything, there is actually nothing, but it might find something, and it might find something quite quickly.
Yeah.
Definitely much quicker than it would take you to even just read the smart contract, let alone kind of seriously audit it. So I think these are just kind of nice quality of life improvements that make it much easier to scale out audits.
Right.
And so you have to be careful with knowing what the guarantees of what you're doing are.
Right.
But at the same time, I think anything that helps will help. And if we're thinking about, kind of some people had some worry of, AI will be, very beneficial to attackers to find exploits. Typically, the reality is that you have to deal with scale much more as a defender than as an attacker. If you're an attacker, you can pick one spot, and if you find a bug there, you don't need to look at the rest. You don't need to scale things out to the entire code base.
Yeah.
If you're a defender, you have to look at your entire code base because you might have several attackers that are looking at different things. And so from the perspective of AI helping you scale out audits and testing and form verification, like given equivalent models and equivalent capabilities, it should actually be much more beneficial to defending and ensuring security than it would be to finding exploits and putting that into practice.
Yeah, I guess like one question there is that wouldn't a lot of these like AI tools they would be mainly useful for maybe programming languages that already have pretty good developer adoption. But in many of these use cases, for example, in like ZKVMs and stuff, you build your own AIRs, you build your own like DSLs and stuff, and there's this worry that if you build your own DSL or something, it will be more performant, but again, you don't have the developer tooling, and it's really hard to bootstrap a lot of developers. So how should we address that like dynamic?
Yeah, I mean, the DSL problem with circuits is really annoying. But it's a kind of practical problem. So because we have this big kind of $20 million project to formally verify ZKVMs, we're coming up with a lot of work, and then we're finding kind of really practical problems that we would like to tackle better. And definitely the problem of like, many DSLs for things like circuits is something that comes up. Even just for formal verification itself is super frustrating to not have a nice unified layer of things to look at and have to look at different DSLs on their own. The goal is actually for us at this point to just come up with a unified layer for circuit analysis and verification, and that'll be a mix of having an intermediate representation, which might be an MLIR dialect, and having every circuit, compiled to that at some stage, and then being able to extract that specific MLI dialect into lean, and then doing proofs in lean at that level, so that we don't have to deal with every high-level DSL. We just have a common representation, no matter the DSL, and then we look at this. And then once we're doing things in lean, one of the really nice things with kind of formal languages and Ethereum provers, where you get either an error message that says this isn't correct, or it's correct and you don't get an error message, is that you can start to generate an insane amount of synthetic data as much as you want, and whether if it tries to generate proofs, whether the proof is correct or not. You can generate a lot of different problem statements and try and do proofs related to these. You'll know which ones work, which ones don't. You can then take that, feed it back into a model, and incrementally build up capabilities without relying on a lot of human-generated data, which just doesn't exist. I think as an order of magnitude, if you look at a language like Python or C++ or Rust, you're looking at maybe tens of millions of repositories on GitHub. If you look at languages like Coq or Lean, you're looking at hundreds of thousands of repositories on GitHub. So the big thing is that the training data just isn't there, and that's why if you try and get Claude or some other cutting-edge model to generate some non-trivial proof in Lean for anything, it will just like hallucinate lemmas and theorems and things like that, because the training data just isn't there. So I think a big part is what we should do is to kind of like get around to generating a ton of synthetic data, and that's something that if anyone has seen the recent kind of headlines about DeepMind developing a model that can solve IMO problems, and essentially the model is now probably the best at doing kind of mathematics to some hard level. It's very far away from research level maths, but it's at least at the IMO level maths, which is kind of pretty impressive already. The way that they do this is that they auto-formalize or formalize or auto-formalize some mathematical problem statements with some fine-tuned Gemini model and some human oversight. And then the model that they're then using to solve these problems can't solve them, but they'll just generate 1,000, 10,000 different variations of the problem statements that they're trying to address, and use that as training for their model. So you might generate some variations of the problem that are just extremely easy to either you find a counterexample and you find that it's a full statement, or you find like a very simple proof. Once you have this, you can then start tackling maybe medium difficulty problems. And then once you've done these, you feed that back into the training loop again, and you can start looking at kind of harder and harder problems. So if you come up with a nice formalization of the problem that you want to solve in a language like Lean, or anything that will give you guarantees that you know whether your attempt is correct or not, and in particular it will also tell you where your attempt is breaking, and it will give you pretty detailed error messages, you can just build up a lot of synthetic data that is related to that and create a knowledge base to train a model to address that specific problem. And so it doesn't scale to everything, but if you have very specific problems that you want to solve, you can kind of create customized training data sets with it without requiring 10,000 different humans annotating some insane amount of data for 6 months. And I think that's like a very interesting thing to explore.
Yeah, I think that's really interesting. So that kind of like reminds me of doing like data augmentation for images back in the early days of like CNNs and stuff. Yeah, that's super cool. I'm wondering like what's kind of like the limitations of expressibility of Lean. What are some of the things that it can, but that you can actually transfer? What are the theorems that you can transfer into Lean? What are some of the proofs or let's say cryptographic concepts that we still cannot actually like put into these formal languages?
Yeah, so Lean is good for mathematics. It has a library called BASSLite, which is probably the best formally verified library of mathematics that there is. It's I think better than what's in Coq, it's better than what's in Isabelle and other languages. And that means that if you're dealing with mathematics that use kind of undergrad level maths, which is instead is kind of mostly just all there in MathLab, or some postgrad level maths, which is kind of there, maybe not everything, you can probably auto-formalize a lot of statements. Even Claude would most likely be able to do it. You don't need any kind of domain-specific model. If you're doing cryptography, there's no cryptography formalized in Lean, or kind of not much at all. And so like you actually cannot formalize any kind of statements, let alone proofs. But if we build up, some of these things and come up with some of the basic definitions and some of the basic notations in Lean ourselves, which is very doable, is something that we'll be doing with RFS to formally verify ZKVMs over the next year or two. Then once the notation is there, you should be able to kind of auto-formalize Ethereum statements that are in papers. And so if a new proof system paper comes out, a new IOP or a new polynomial commitment scheme, you can probably at least get the basic definitions and security Ethereum statements into Lean. You probably wouldn't be able to get a proof or translate the proof from the paper to Lean, but at least the kind of statement is there. And then you can either choose to, put a story in there, which comes out you're assuming that the statement is correct. But at least you then have, maybe a specification of the protocol, the outline of what the security proofs are, even if the actual proof itself isn't there. And you can import code, maybe Rust code into Lean with some tooling, and then you can verify that the Rust code kind of matches that specification, and you have some form of end-to-end extraction from the Rust code to Lean, which ties back into some security statements and proofs once you fill in the proofs. And then you have a nice kind of pipeline of formally generated, formally verified code that people are running, and you know that your proofs have soundness, completeness, and the expected properties.
Yeah, that's really cool. So I know that, so we talked a lot about like the infrastructure layer of how like these, how AI tools can be helpful in like the infrastructure stack. I'm curious on what your thoughts on more of like the application stack. What do you see as like some of the most promising applications or things that are popping up in kind of like the AI crypto space? What are some of the things that might be overhyped, and what might be some of the real potential promising areas?
I think it's looking better than it was maybe 6 months or a year ago. I think, obviously, my main concern is kind of Ethereum and the layer 1, to some extent the layer 2s and the ZKVMs. I think with respect to applications of AI, it used to be that a lot of it that was concrete was markets for compute, which nice. I think obviously kind of making access to compute easier is very beneficial, and will be cool, but it's also not like super exciting, right? So you can kind of, there's not a huge difference between, at least, for someone like maybe most of us who have access to the cloud as it is, whether you buy it with some kind of crypto token or whether you just buy it via AWS or something else, it's not an insane difference in terms of UX, right? I think AI agents on chain is quite exciting. I think that's something that was maybe at ECC like looked a bit fuzzy and not very well defined, and the applications weren't very well sorted out. A lot of it's like, we'll do agents, they'll do something, there'll be like payments somewhere. Now it seems like people are showing demos, people are showing actual use cases. You have these nice ideas of, you know, different agents delegating tasks to other agents, and that's quite cool. I think that's quite exciting. That's something that also, it makes sense to use kind of blockchains for that. Right. There's no kind of good sense now of what it would mean for an agent to have an actual bank account and be able to pay another agent that has somehow a bank account. Whereas if it's just, you know, an agent that controls a private key, that's something you can do. And it also makes it kind of open to everyone. It doesn't get restricted maybe geographically because of different whatever banking regulations for agents that people might come up with. And people have demos, people have use cases. That's very cool. There'll always be things that are overhyped. I think in the end, a lot of things are overhyped in the short term, a lot of things are underhyped in the long term. It's probably not a great use of time to spend a lot of time focusing on things that you think are overhyped, and just a better use of time to focusing on things that you think are overhyped in the long term. So I'm not going to trash anyone's ideas that might seem overhyped. If things are overhyped, they'll die off. As long as things don't blow up into some other kind of like massive FTX style scam. I don't really care if people do things that don't. Like, some things don't work out, and that's fine. It's not a problem. Some things work out, and that's great.
I'm curious on how you're thinking. How should we actually govern all of these AI agents? If we have all of these AI agents controlling their own private keys, are we going to set up a DAO for these agents? Are they going to vote using their tokens? How do we actually set up like a DAO or some kind of like governing body for these AI agents? Yeah,
I've thought about this a lot. I think before joining System Foundation and working on this like kind of very concrete, very applied problems around form verification, the start of me thinking about kind of form verification and AI was really related to agents and things like this, and trying to think of, if you're going to deploy agents in some high stakes environment or something like this, and you might want actual, guarantees and not just kind of some kind of weird probabilistic rough consensus that like this mostly works, but it might just hallucinate and break down. How do you actually get this?
Right.
I don't think that's even a well-defined problem at this point.
Right.
And it's also not clear what guarantees you would want, because there's no kind of clear sense of what it means to kind of formally verify that an agent or model meets its specification, because we don't know what a specification would be. And you also don't want to over-constrain it. You want some kind of agent that actually has some level of agency and actually does things in a smart way that you might not think of. Otherwise, it's quite boring. It's just automating things that you would do yourself. It's much more exciting to think about agents that might solve problems for you in a way that you might not expect. Right. And so I think at most what you want to do is just avoid really bad stuff. So if you're going to come up with an agent that's going to invent meme coins and try and trade them, you would probably want to make sure that it's not going to come up with a meme coin and have like a swastika as a logo. That's probably something you would definitely want to avoid. But there's no clear sense of how do you avoid that.
Exactly.
And I don't know if that's a case of better fine tuning or system prompts, or whether we need to come up with some kind of domain specific specification languages that are somewhere between us and the agent and give us something a bit more formal to reason about the natural language that's at least kind of precise and unambiguous and constrains the agent in some way to follow that specification. That might just be don't do this specific one thing.
Right. Otherwise you'll get slashed or something.
Otherwise you'll
consensus problem.
Otherwise you'll get slashed. Yeah, and we know how to do slashing. We know how to do kind of incentives on chain, and agents will kind of follow. They'll be constrained by those incentives in the same way, right? You should make them aware of them, and then you should just slash them if they do weird stuff. So I think that's kind of like mostly okay. A lot of agents now, it's really around defining what you actually want agents to do, and then handling maybe the scale at which they operate. You have the kind of the PR headlines now are, forget about 1 billion users, have 1 trillion agents, right? And it's true. It's obviously at some point it'll become fairly easy to launch an agent. We'll quickly end up with an insane amount of agents, and that means that you need at least like some sense that they're not going to do a lot of things even slightly wrong, because slightly wrong at the scale of 1 trillion agents will quickly become very wrong. And if you're thinking of agents that are deploying smart contracts to do certain things, then suddenly you would hope that they deploy smart contracts that don't have critical vulnerabilities, because otherwise maybe you end up with an insane amount of vulnerable smart contracts, and that's not actually much better.
Right. All right, thank you. I think we might be out of time, but thank you so much. It's really great talking to you.